সো আজকে আমরা পড়বো হচ্ছে রিঅ্যারেঞ্জমেন্ট রিয়াকশানস বাই গ্রিন অ্যাপ্রোচ, কারণ আগের দিন আমাদের ফিডেলক্রাফট রিয়াকশান অবধি পড়া হয়েছিল, তাই তো? সো রিঅ্যারেঞ্জমেন্ট রিয়াকশানরা গ্রিন কেমিস্ট্রির দিক থেকে একটা ইউনিক জায়গা আছে, কারণ গ্রিন কেমিস্ট্রি তো সাস্টেনেবল কেমিস্ট্রি এবং সেখানে অ্যাটম ইকোনমি ব্যাপারটা খুব ইম্পর্টেন্ট, যে কটা অ্যাটম আমার রিয়াক্ট্যান্টে আছে আর ফাইনালি কটা অ্যাটম আমি আমার প্রোডাক্টে পেয়েছি। যদি সেটা যে কটা অ্যাটম নিয়ে শুরু করেছিলাম সব কটা অ্যাটমই যদি থাকে আমার প্রোডাক্টে, তাহলে সেটা 100% অ্যাটম ইকোনমিক বলা হয়। অ্যাটম ইকোনমি নিশ্চয়ই তোমাদেরকে স্যার পড়িয়েছেন। তো রিঅ্যারেঞ্জমেন্ট রিয়াকশান হচ্ছে এমন একটা এক্সাম্পল, যে কোনো রিঅ্যারেঞ্জমেন্টই যেখানে স্কেলিটাল রিঅর্গানাইজেশন হয় কিন্তু কোনো অ্যাটম এদিক ওদিক দিয়ে বেরিয়ে যায় না, যদি না রিঅ্যারেঞ্জমেন্টের সাথে অন্য কোনো জিনিস অ্যাসোসিয়েটেড থাকে। যেমন পিনাকলন রিঅ্যারেঞ্জমেন্টে কিন্তু ডিহাইড্রেশনও হয়, তার সঙ্গে সঙ্গে রিঅ্যারেঞ্জমেন্টও হয়। অতএব সেখানে স্টার্টিং ডাইঅল এবং ফাইনাল পিনাকোলন প্রোডাক্ট বা যে কিটোন কম্পাউন্ডটা তৈরি হয় সেইটাকে তুমি 100% অ্যাটম ইকোনমিক বলতে পারবে না, কারণ সেখানে জল বেরিয়ে গেছে, দুটো এইচ আর একটা অক্সিজেন বেরিয়ে গেছে, এবং তার সাথে সাবসিকুয়েন্টলি রিঅ্যারেঞ্জমেন্টও হয়েছে। কিন্তু যদি আমি ফ্রাইজ রিঅ্যারেঞ্জমেন্ট বা আমাদের ক্লেইজেন রিঅ্যারেঞ্জমেন্ট এই ধরনের রিয়াকশানের কথা বলি, পার্টিকুলারলি ক্লেইজেন রিঅ্যারেঞ্জমেন্ট, যেটাকে আমরা অ্যালাইল ফিনাইল ইথারেরকে হিট করে রিঅ্যারেঞ্জ করিয়ে অর্থ বা প্যারা অ্যালাইল ফেনলিক ডেরিভেটিভস বানিয়ে থাকি, সেগুলো 100% অ্যাটম ইকোনমিক। তো সেই রেসপেক্টে রিঅ্যারেঞ্জমেন্টদেরকে আমরা আলাদা করে পড়ছি। প্রথম যেটা পড়বো সেটা হচ্ছে ফ্রাইজ রিঅ্যারেঞ্জমেন্ট। তো অ্যারোমেটিক ইলেকট্রোফিলিক সাবস্টিটিউশন পড়ার সময় আমরা দেখেছি যে আমাদের ফেনলিক কম্পাউন্ডটা অ্যাম্বিডেন্ট নিউক্লিওফাইল, এবং সেই জন্য তার ওপরে কোনো অ্যাসিটাইলেশন গোছের কিছু করতে গেলে কার্বনে অ্যাসিটাইলেশন হওয়ার বদলে অক্সিজেনে অ্যাসিটাইলেশন হয়ে যায়। অর্থাৎ ফিডেলক্রাফট রিয়াকশানটা কিন্তু ফেনলের ওপরে খুব একটা সাকসেসফুল হয় না। আর ফেনলের ওপর অ্যাসিটাইলেশন করতে গেলে ভায়া ফিডেলক্রাফট AlCl3-র সাথে ফেনল কোঅর্ডিনেট করে বসে থাকে এবং রিংটা ডিঅ্যাক্টিভেটেড হয়ে যায়। তার ফলে সেই জায়গায় ফার্দার কোনো অ্যাসাইলিয়াম ক্যাটায়ন বা কোনো অ্যাসাইল স্পিসিসকে ঢোকানো একটু ডিফিকাল্ট হয়ে পড়ে আমাদের পক্ষে। অ্যাট দ্য সেম টাইম ফেনলের যদি প্রপারলি অ্যাসিটাইলেশন করতে হয়, তাহলে ফেনলকে আমরা জেনারেলি একটা অ্যাসিটাইলেটিং এজেন্ট নিই, লাইক অ্যাসিটিক অ্যানহাইড্রাইড বা এই ধরনের কিছু, বা অ্যাসিটাইল ক্লোরাইড, এবং তার সাথে পিরিডিন দিয়ে আমরা একটা নিউক্লিওফিলিক অ্যাডিশন এলিমিনেশন মেকানিজমের থ্রু দিয়ে ফেনল থেকে ফিনাইল এস্টার বানাতে পারি। ফরচুনেটলি এই জাতীয় ফিনাইল এস্টারকে যদি AlCl3 দিয়ে হিট করা হয় এবং তারপরে আমরা সেটাকে যদি ওয়ার্ক আপ করি, তাহলে ইভেনচুয়ালি আমাদের অর্থ এবং প্যারা অ্যাসাইলেটেড ফেনল ডেরিভেটিভ পাওয়া যায়। AlCl3 মিডিয়ামে এই ফিনাইল এস্টারদের যে রিঅ্যারেঞ্জমেন্ট, সেটাকে বলা হয় ফ্রাইজ রিঅ্যারেঞ্জমেন্ট। এটা তোমার মনে আছে তো?
হ্যাঁ স্যার, মনে আছে।
ফেনলিক কিটোন তৈরি করার ওয়ান অফ দ্য রোবাস্ট টেকনিক। এটা দুটো রিয়াকশান কন্ডিশনে এটাকে করা যায়। এটা আমি সেমিস্টার 4-এর যে স্টাডি মেটেরিয়াল সেইটা একটু পুল আপ করলাম, কারণ আমরা ফেনলিক এস্টার যখন পাচ্ছি তখন সেটাকে যদি AlCl3 দিয়ে রুম টেম্পারেচারে রেখে দিই, তাহলে সেটা প্যারা পজিশনে চলে যায় অ্যাসাইল গ্রুপটা মাইগ্রেট করে। কারণ দেখো এই রিঅ্যারেঞ্জমেন্টটা যে অ্যাটম ইকোনমিক সেটা দেখা যাচ্ছে, কারণ এখানে একটা হাইড্রোজেন ছিল, আমরা এই হাইড্রোজেনটাকে অ্যাজিপ এইখানে নিয়ে চলে এসেছি অক্সিজেনের গায়ে, আর এই অ্যাজিপ এখানে চলে গেছে। এটা অবভিয়াসলি এরকম সিম্পলি এক্সচেঞ্জ টাইপের রিয়াকশান নয়, তার মেকানিজম অন্যরকম, এবং সেগুলো যখন আমাদের পড়ার কথা ছিল আমরা ডিসকাসও করেছি। কিন্তু অ্যাটম কোনো কিছু লুজ হয়নি, কোনো লুজ করিনি কিছু। ওই একই রিয়াকশান যদি আমরা হাই টেম্পারেচারে করি, তাহলে ওটা অর্থ পজিশনে গিয়ে বসে যায়, এবং এইখানে আমরা অর্থ এবং প্যারা প্রোডাক্টের ফর্মেশনের ডিফারেন্ট মেকানিজমস দেখিয়েছিলাম। সেখানে ইন্টারমলিকুলার মেকানিজম ছিল, সেখানে ইন্ট্রামলিকুলার মেকানিজমও ছিল, এবং ফ্রাইজ রিঅ্যারেঞ্জমেন্ট অ্যাকচুয়ালি এমন একটা রিঅ্যারেঞ্জমেন্ট যেখানে দুটো মেকানিজমই অপারেট করে। আমরা যদি ইন্ট্রামলিকুলার মেকানিজম দেখাই, তাহলে সেটা একটা পাই কমপ্লেক্সের থ্রু দিয়ে অ্যাসাইলিয়ামের মাইগ্রেশন দেখাতে পারি, অর্থ অ্যাটাকটা সেইভাবেই হয়। আর যদি ডিরেক্ট অ্যাসাইলিয়ামকে বের করে দিই, এখান থেকে যদি অ্যাসাইলিয়ামকে ডিটাচ করে বের করে নিয়ে আসি, তাহলে আমাদের অর্থ প্রোডাক্ট এবং প্যারা প্রোডাক্ট একটা সিম্পল অ্যারোমেটিক ইলেকট্রোফিলিক সাবস্টিটিউশনের থ্রু দিয়ে যেতে পারে, এবং অ্যারোমেটিক ইলেকট্রোফিলিক সাবস্টিটিউশনের সব ক্যারেক্টারিস্টিক্স এখানে বজায় আছে। তুমি যদি রিংয়ের ভেতরে খুব হাইলি ইলেকট্রন উইথড্রয়িং সাবস্টিটিউয়েন্ট দিয়ে দাও, তাহলে কি রিয়াকশান হবে? রিয়াকশান কি হবে? আচ্ছা, তোমাকে আমি একটা দেখাই, এই একটা দেখাই, এইটা আমার কাছে ছিল, এই দেখো, এই প্রবলেমটা মনে আছে? এটাকে 4 ইকুইভ্যালেন্ট AlCl3 দিয়ে রিয়াকশান করেছে, দুটো মাইগ্রেশন হতে পারতো, এটাও এদিকে মাইগ্রেট করতে পারতো, এটাও এদিকে মাইগ্রেট করতে পারতো। ফাইনাল প্রোডাক্টে দেখো কটা মাইগ্রেট করেছে? একটা। তার কারণটা কি? একবার মাইগ্রেশনের পরে, কারণটা কি? কারণটা হচ্ছে ওয়ান্স দিস গ্রুপ হ্যাজ মাইগ্রেটেড, এই রিংটার কি হয়েছে? এই লাল রঙের গ্রুপটা কি?
ডিঅ্যাক্টিভেশন হয়ে গেছে।
ওটা তো ইলেকট্রন উইথড্রয়িং গ্রুপ, তাহলে ইট ইজ ডিঅ্যাক্টিভেটিং দি phenyl ring towards further aromatic electrophilic substitution, and therefore the second acyl group does not get the chance to migrate. মনে পড়েছে? এবং এইটা সেই একটাই একমাত্র এক্সাম্পল ছিল যেখানে আমরা দেখিয়েছিলাম যে ইউ ক্যান ইনফ্যাক্ট গেট লটস অ্যান্ড লটস অফ ক্রস প্রোডাক্ট। জেনারেলি রিঅ্যারেঞ্জমেন্ট রিয়াকশানস দ্যাট উই হ্যাভ সিন, হফম্যান বলো, কার্টিয়াস বলো, schmidt বলো, বেকম্যান বলো, বেকম্যানে তাও একটা ফ্র্যাগমেন্টেশন অনেক সময় হয়, ওয়াগনার মিরুইন বলো, যাই বলো, যেখানে প্রশ্ন ভরিয়ে ভরিয়ে আসে, almost all of them are strictly intramolecular and we do not expect formation of cross product. But Fries is one notable example in our syllabus যেখানে আমরা ক্রস প্রোডাক্ট তৈরি হতে দেখেছিলাম, বিকজ both the intra as well as the intermolecular mechanism is operating here. And we also talked about the temperature dependence. At 25 degrees centigrade, it is the para product which is forming, because the transition state associated with the formation of the ortho product is key, relatively unstable. কেন? Why? Why is transition state leading to the ortho product relatively unstable compared to that leading to the para product? অর্থ বললেই, হ্যাঁ, অর্থ বললেই যেটা মাথায় আসে, উই অলওয়েজ থিঙ্ক অ্যাবাউট স্টেরিক ক্রাউডিং, যে স্টেরিক ক্রাউডিং আছে, অতএব দেয়ার ইজ ডিস্টেবিলাইজেশন অফ দি ortho transition state, and therefore at low temperature, when the reactions are irreversible and the product mixture is guided by the rate at which 2 different or 3 different products are forming, that means under kinetic control it is the para product which is the dominant one. But if you increase the temperature at 165 degrees centigrade, or even you can take the para isomer and you do the reaction in presence of AlCl3 at 165 degrees centigrade, again the migration is seen to be taking from either from oxygen to the ortho position or from the para position to the ortho position, depending upon which is your starting material, whether this one is your starting material or that one is your starting material. At this temperature all of the reactions are reversible, and therefore the thermodynamic product, the product that is thermodynamically more stable, dominates the product mixture. Why is the ortho product thermodynamically more stable even though there is steric crowding?
Hydrogen bonding possible. OH এর সাথে C double bond
Yeah,
O
yeah, you can see here intramolecular hydrogen bonding is there, but to be more precise, I would say that in the reaction medium there is no hydrogen on oxygen. What this oxygen carries is basically an AlCl3, and when the keto is at the ortho position, it can, the phenolic ketone can act as a bidentate ligand and form a chelate complex which stabilizes the ortho adduct compared to the para adduct where there is no possibility of formation of such chelate. So in one sense your answer is right, that finally when we work up with acid, it is the intramolecularly hydrogen bonded ortho isomer which should be thermodynamically more stable. But in the course of the reaction, we should probably rationalize the formation of ortho product as the major product by citing the formation of the chelate complex, because under this condition the oxygen does not carry the hydrogen required for intramolecular hydrogen bonding, rather it is attached to an aluminum, and therefore it has a greater chance of forming a chelate when the CO is at the ortho rather at the para. বোঝা গেল?
হ্যাঁ
So this is our background information regarding fries, and I have not chosen to include these things here, but we know this thing that this can happen. And one particular example you can consider where carbon disulfide is being used as a solvent, anhydrous AlCl3 is being used as the catalyst, and you are giving lots and lots of heat so that the ortho and para product are forming, and probably this one will be the major product under heating condition. And then for workup you have to remove the solvent, and then to break the chelation or the oxygen metal bond you have to use dilute HCl. So we are saying that this is catalyzed, but this is not truly catalyzed because oxygen এর সাথে aluminum is already associated, and therefore you need stoichiometric amounts of a Lewis acid such as AlCl3. You can change this AlCl3 to another Lewis acid or a Bronsted acid such as HF. HF is industrially very important to carry out Fries rearrangement, but use of hydrofluoric acid comes with its own baggage. That means you have to have special type of containers and special techniques to handle that kind of a hazardous and toxic substance. But industry can afford that because they invest a lot of amount first, and then they reap the dividends throughout the tenure of the reactor or something like that, because they do reactions in such a large scale that their profit cost analysis is totally different from something which you are supposed to do in a 100 ml round bottom flask. So that's something different, and industrial processes heavily use hydrogen fluoride with proper precaution obviously, so that is a tedious job. So these things are associated with certain disadvantages or the so-called non-green contexts. First of all, we should not call this catalyst, but the common verbology is catalyst, so we go with that narrative, but we know that this is not actually a catalyst. You use stoichiometric amount of AlCl3, and after you work up it forms aluminum hydroxide. So the problem as we faced in traditional Friedel-Crafts, where the same AlCl3 is being used as the catalyst, we also face the same problems because these are not environment friendly. These are detrimental for the sustainability of environment, and they cause disposal problems, and to take care of those problems properly the process become cost ineffective. If you are doing the reaction under conventional heating, then you are expending non-renewable energy, which is not good for sustainability as well. The reaction condition is pretty harsh and the yield is not very good. Low to moderate yields, or for heavily substituted acyl compounds the yield is not good at all. And we also need to remember that if you have already present some functional group which reacts with AlCl3 or something like that, then your substrate scope is very much limited. You can't do the reaction. Separation is required sometimes, because the yield of the ortho and para can sometimes be variable, and by tuning the temperature you can make one major, the other minor, but still the minor product has to be separated, and that can be sometimes quite tricky. These severe reaction conditions imply that you can only use esters that do not have any substituent that is reactive under those reaction conditions. So your substrate scope is pretty limited, as I have already told you. The temperature that is required for the reaction, if you are looking particularly to achieve orthomigration, sometimes chars the products and decreases the yield, and the mixture of regioisomer formation, as I have told you, it is certainly a problem. So this thing is associated with a lot of difficulties, and chemists have done their best to come out with sustainable alternatives, greener alternatives of Fries rearrangement. And here we highlight some of these. When browsing through the literature, I was a little bit surprised to see that the number of modifications done for Fries rearrangement is quite a bit less compared to other reactions like aldol, Novenagel, etc., etc. Claisen, not Claisen rearrangement. Also, Claisen rearrangement also has many variations, as you will see. But the number of variations for Fries is relatively less. There could be two reasons behind it. One is this reaction is not as important as the reactions that I have mentioned, because Claisen condensation, Michael reaction, aldol chemistry, those are probably much more important reactions than this Fries rearrangement in terms of the number of molecules that we can get from those named reactions. And the second point could be that the traditional method, the effectiveness of the traditional method is yet to be surpassed. But the most important modification of Fries rearrangement is to carry out the reaction under photochemical condition, something which is known as the photo-Fries rearrangement. In this condition, UV light is your reagent and you do not need any catalyst. So that's good. You are avoiding the use of the toxic AlCl3. And under this condition, the reaction mechanism is also completely different. The reaction proceeds via formation of the carboxylate radical. So what happens is, not carboxylate radical, but acyl radical. It should be acyl radical. So something like this happens, RCO dot. So you have your phenyl ester. When you hit it with proper wavelength of light, then this bond breaks and generates a phenoxyl radical and a acyl radical. If you draw the resonance structure of the phenoxyl radical, which is something like this, let me draw the radical structure of the phenoxyl radical. So suppose you have something like this. You have one lone electron here there, and of course other electrons are there which I am not drawing. But if you draw the resonance structure, where should you expect the lone electron to go? At these positions, right? You can draw the fish hook arrows and so on. So eventually you are going to end up with here, and then here. And when this thing, which has detached itself from the phenoxyl, and it is, the geometry is not okay because this is sp hybridized, but let's say it combines with this one, what is the product that you should get? Eventually ortho product, right? And if it combines with this one, what is the product that you should get?
The para product.
A para product. And this is how the reaction goes. And by tuning the reaction condition, you can in fact tune the regioselectivity, which one is the major product, which one is the minor product, etc. There are several examples of photo-Fries rearrangement, and the most important part is that you can do this reaction in at room temperature under very mild reaction condition, completely avoiding the detrimental catalysts, gives you a huge benefit. Say for example, I have cited one case study. You have this compound, okay, this one itself is a product of Fries rearrangement of phenyl acetate. Now you are acetylating in presence of pyridine, the OH is again being acetylated, and therefore you have a phenolic ketone and an ester. an aromatic ketone, and the phenol part is esterified. Now you are protecting this ketocarbonyl by forming an acetal. We also have one carbonyl here, but it does not react, while this one does. Why? Why is that?
কারণ কার্বন
The reacting one is more electrophilic.
সিঞ্জিন বলো।
কার্বনিল বেশি রিঅ্যাক্টিভ, বেশি ইলেকট্রন।
কার্বনিল তো দুটোই।
ও
তুমি আরেকটু স্পেসিফাই করে বলো।
মানে কিটোন পার্ট,
হ্যাঁ।
কিটোন যেটা ওখানে তো আরেকটা এস্টার অক্সিজেন রয়েছে না,
হ্যাঁ,
তো
মানে
ওটা তো অলরেডি ইলেকট্রন ডোনেশন পেয়ে যাবে।
so the electrophilicity of this carbonyl is considerably less compared to the electrophilicity of that carbonyl. This is a ketocarbonyl, whereas this is a ester carbonyl, and therefore this thing has what is known as কি আছে ওর, the plus R effect, right? So you have the plus R effect which stabilizes the ester and reduces its electrophilicity, and therefore it is not surprising to have this one as my protected product. And now see, no AlCl3, nothing. In hexane, in presence of a base like K2CO3, they are irradiating this thing with proper wavelength of light, UV light. See what has happened? Migration of the acyl group or acetyl group from oxygen to the ring carbon, and then with aqueous acid workup you can release the ketocarbonyl, so that you end up with a diketo derivative of the phenol. I have one more question for you before leaving this case. One more question. If I hit this thing with H nu, then no reaction takes place. But I have to protect the carbonyl and then do the photophrase and then deprotect. It would have been better if we could avoid the protection deprotection steps. Why is this thing not working? What do you think? What is your
Deactivation.
deactivation due to what?
Because the NECO6.
This group is present attached to the carbon attached to the ring carbon, and it has minus R and minus I effect, right? Therefore this is a strongly electron withdrawing group, and as we have seen, Fry's rearrangements do not generally take place under such condition where the ring contains deactivating substituents, right? But if you manage to acetylize this thing, it is still electron withdrawing, but does it have minus R effect?
No.
And therefore the electron withdrawal has decreased, the deactivation has decreased, and the migration from oxygen to the ring carbon is made possible. And finally we have to achieve our target, we have to use aqueous acid. Okay, get it? ঠিক আছে তো?
Yes, sir.
So that's a photophrase. What is the green context? Mild, very mild reaction condition. You are doing the reaction at room temperature, neutral reaction medium, so no acid, almost no acid, or practically no base is present, because potassium carbonate is sort of a weak base. And therefore if you are doing the reaction at room temperature, the reaction is not expending that much of energy as well. Substrate scope expands because you are doing the reaction at milder condition. No catalyst is required, and the yield of the reaction product is very high, and therefore these are the benefits or the greener payoff that you can have if you modify the reaction condition from the traditional aluminum chloride induced reaction to photophrase. Okay, then they have done another variation of this reaction where phenyl acetate is converted in 88%, very high yield, it's exclusively, almost exclusive formation of the para product, if you are doing the reaction in K10 clay, which is also known as the Montmorillonite clay, which is basically aluminum magnesium silicate. There is quite a large formula for this compound, but it's basically an inorganic silicate, and within this inorganic silicates there are pores, inside which the organic molecule can take refuge and can do the reaction. So avoiding the traditional AlCl3 catalyst and also using a catalyst which is reusable. You can use this catalyst again. You can just purify the product and then purify the catalyst just by physical methods, and you can reuse the catalyst. So that is again another aspect of the sustainability. But for sure the reaction condition is not ideal because you are spending a lot of energy here, you are also spending a lot of time here. So not totally green, but better than AlCl3. So this green context is that you mix the phenyl acetate with K10 monopolymerate clay, so that's a solventless reaction, and the reaction is of high regioselectivity because the para product is forming at a much higher amount compared to the traditional AlCl3 catalyzed method. The catalyst reusable use of AlCl3 is avoided. However, the temperature and pressure is not ideal. I have managed to find this reference, but maybe using different clays and different medium, you can optimize the reaction condition so that these two parameters can be further optimized. Okay. Now they have done what is known as a considerable rate enhancement of rice rearrangement in commercial microwave over conventional methods. A mixture of paracrysyl acetate. See that this is paracrysol, right? And you have acetate because this is a ester of acetic acid. Paracrysyl acetate, AlCl3 is mixed in chlorobenzene medium. That is not ideal because you should like to avoid the chlorobenzene, but here it is imperative. But the benefit is that under a sealed tube under microwave oven for 2 minutes it gives you 85% yield of the product. So just 2 minutes heating would give you this compound. I have written this 2' and 5' before the hydroxy and methyl. Why not 2 and 5? Yeah, then what is the 1 position? Not 1'. What is the 1 position? This one. And this one is 2, right? And this one is like 1', right? And this one is 2', right? Then this is 3', 4', and this one is 5', right? So do not make that mistake, okay? People tend to make this mistake very much, that people call it 2,5-dihydroxy 2-hydroxy 5-methyl-acetophenone. That compound does not exist actually. That compound does not exist because there is no position 5. If you had long chain here, then probably you would have a C5 there, but here it is absent. So reaction is done with very short time, only 2 minutes. Renewable energy source, that's good for us. Waste treatment and disposal problems are also minimized. I have managed to find one recent example. This one is as recent as in 2023, and that's they have demanded. I have not checked or verified, but certainly because they have published in a reputed journal, I think their demand is valid. That this is the first mechanochemical Fries rearrangement. Mechanochemistry means you are grinding the reactants together. So they have taken like phenyl acetate. They have done many things, but I have taken only one example, phenyl acetate, and they have done this reaction under 2 different conditions. One is the ball mill, where they have tried the liquid assisted grinding, that they have taken this thing in a mixture of AlCl3 and sodium chloride, which is supposed to provide a base for the grinding. And this is a vibrational mill inside a 50 ml zirconium dioxide vial for 90 minutes with a frequency of 50 kilohertz. The mechanical grinder is grinding that thing, and just a little bit, a few microliters, maybe 500 microliters of nitrobenzene is added into this to facilitate the grinding, and after their workup they are getting high yields of these 2 compounds. They have also done this thing in something which is known as stainless steel extruder. If you are interested, you are most welcome to look these things up. These are engineering marvels that are available in high-tech laboratories around the world, So extruder is something where you mix everything up and you give the instruction to the instrument for a certain RPM for a certain time. The computer processes the information and the machine does according to the instruction that you are providing, and finally the extruder extrudes. Extrude মানে কি? বের করে দেওয়া, right? Like it extrudes. Once the reaction is done, it extrudes the product, and this reaction is a continuous flow method where many chambers are actually lined up. But at this machine, this reaction can be done at ball mill at room temperature, but here you need a little bit of higher temperature, and then your workup will give you the regioisomeric mixture, but those things are actually tunable. So what is the green context? Relatively shorter time compared to the classical method, can be done at room temperature if you are going for the ball mill process, which means it's energy efficient. In ball mill it is almost solventless, not totally solventless because a little bit of nitrobenzene you are using, but it is much better compared to using a whole lot of chlorobenzene or carbon disulfide. If you can get away with using just a few mLs of solvent, then it's almost solventless. Waste treatment and disposal problem is also minimized. Regioisomer ratio that I have not written here, it can be manipulated by variations of the additives that what you are adding inside the reaction medium, or the liquid that you are using for the liquid assisted grinding. You can change those things, change those parameters, and be perfectly okay with the regioisomeric ratio. You can have different regioisomeric ratio. So this concludes our green fries rearrangement. Any of you have any questions? So can we move on to the next reaction? That is again another known reaction to you. That's Claisen rearrangement, right? Claisen rearrangement is, we have learned Claisen rearrangement in terms of only the aromatic Claisen rearrangement. Have you learned about the aliphatic Claisen rearrangement or some of its variations in your semester 5 classes? aliphatic Claisen টা কি পড়েছিলে? মানে হ্যাঁ 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 মানে পড়লে পেরিসাইক্লিকই পড়বে। মানে আমি এরকম কথা বলছি, দেখো এইরকম জিনিস কি পড়েছো দেখো তো। This one is the substrate for the allyl vinyl ether, right? And if you change this to this one is, এটা কি তুমি এইটা সেমিস্টার 4-এ পড়েছিলে তাই তো, যখন রিঅ্যারেঞ্জমেন্ট রিঅ্যাকশনস পড়েছিলে, আর এইটা তুমি সেমিস্টার 5-এ পড়েছো। সেমিস্টার 5-এ তোমাদের সাইক্লোহেক্সেন ছিল তো, ছিল না? সেখানে এই সব ফর্ম দেখেছো না? এই ফর্মে অ্যাকচুয়ালি আমাদের এই ক্লেজেনটা বেসিক্যালি এরকম সব ট্রানজিশন স্টেটের থ্রু দিয়ে যায়। এগুলো স্যার নিশ্চয়ই পড়িয়েছেন তোমাদেরকে, মনে পড়েছে? ছিল না? এবার এইখানে এর জিওমেট্রির ওপর বেস করে তখন কখনো তুমি সিস পাবে, কখনো ট্রান্স পাবে, এর জিওমেট্রির উপর বেস করে কখনো সিস কখনো ট্রান্স এরকম হবে। দ্যাট এটা কী হলো? Or you can have different substituents here. This can even be a chiral center. So কিছু কিছু তোমার জানা আছে। That knowledge will not be required too much in the reactions that you are doing, কারণ মেকানিজম তোমাদের কাছ থেকে গ্রিন কেমিস্ট্রিতে জেনারেলি চায় না সিম্পল মেকানিজম যদি না হয়, কিন্তু আমরা একটুখানি মেকানিজমটা একবার দেখে নিচ্ছি। অ্যান্ড অ্যাটলিস্ট অ্যারোম্যাটিক ক্লেজেনের মেকানিজম আমাদের এখানে করে দেওয়া আছে, তো আমরা জাস্ট একবার কুইকলি দেখে নেব। এই যে রিয়াকশানটা হয় এটাকে আমরা বলি 3-3 sigmatropic shift, right? This is called a 3-3 sigmatropic shift. What happens is it's a pericyclic reaction where 2 pi bonds are broken and 1 sigma bond is broken at the expense of formation of 2 new pi bonds and 1 new sigma bond. The bond that was between oxygen 1 and carbon 1 is now between carbon 3 and carbon 3 of the allyl chain and the aromatic ring, and thus the reaction stops here, and eventually we get aromatization to give you the corresponding orthoallyl phenol. If on the other hand the ortho positions are occupied and the molecule cannot aromatize, then we have a further 3,3 sigmatropic shift. The name of this reaction is, this is another name reaction. Do you know the name? That's called COPE. When the 3,3 sigmatropic shift involves migration of a bond from oxygen carbon to carbon carbon, that's known as Claisen. And when it is a carbon carbon bond migrates to another carbon carbon bond in the 3,3 manner, it is known as COPE. And the COPE, after the COPE is over, the aromatization step can take over, and I get the para substituted product. So this is the fundamentals of the Claisen rearrangement as we know. So we have given 2 examples here. Any problems with this one or with this one? This one is allyl phenyl ether, or also known as allyl oxybenzene. You get 2 allyl phenol because you have hydrogen at this present here, and therefore there is no problem of aromatization. Here both ortho positions are actually occupied and both are equivalent, so you can migrate the allyl group on this direction or on that direction. Nowhere can it aromatize, and further a COPE rearrangement has to take place to give you the corresponding 4-allyl 2,6-dimethyl phenol. Okay, this was discovered by Claisen in 1912, and sort of an accidental discovery, but let's not go into that story. But this is the mechanism. The slow step is the 3,3 shift, and then the proton transfer, which is not pericyclic, that's ionic step. Aromatization gives you this compound. When migration occurs at the ortho and gamma position, it is this carbon which is attached with that carbon, as evident because we have taken 2 different substituents here. Here there are 2 hydrogens, here I have 1 hydrogen and 1 phenyl, and as you can see, at the ortho position it is the phenyl substituted carbon which is attached, at par with my mechanistic explanation. And if you take an isotopic level here, then also it is the isotopic level which gets attached to the ortho carbon, because our mechanism says so. The earliest record of the Claisen itself happened to be a sort of a green reaction, not done because people wanted to do green reaction, but accidentally, because Claisen's rearrangement was done in dry state. He simply heated the allyl phenyl ether, and that compound is a solid, therefore this is a solid phase reaction, and most importantly he desisted from using any solvent. So this is a solventless reaction. It's one of the earliest example of solventless synthesis, solid phase synthesis. But at that point of time people were definitely not aware of the green chemistry concepts. Green chemistry concepts came maybe 70-80 years after this reaction was discovered, but accidentally that aspect was covered. So what are the non-green context of these reactions? Very high temperature is required, therefore you need to heat it and probably use up a lot of non-renewable energy, and that is not good. Long time, and even then it provides very low yield, about 40%. So they have tried to modify these reaction conditions. Microwave irradiated Claisen rearrangement, and this has been done quite well. At microwave you are using 553 Kelvin temperature, so that's not ideal microwave energy you are expending, but you are expending it for only 5 minutes, so the reaction is much it saves a lot of time. In terms of time resource, you are saving a lot. And at lower temperature, this can lead to complications because sometimes only one of these group migrates, so that's a product mixture that you don't want to deal with. And also some unrearranged product as the major component may turn out. I have one sort of a out of context question for you. Are these two positions equivalent? Are these two positions equivalent? I have chosen to migrate here. Could I choose to migrate here, or would have been different product if I choose to migrate here or not? Think carefully and then provide the answer. Think of this total part as R.
CME.
Sure, because if you migrate here, even if you migrate here, then you just rotate it. Then you just rotate the thing, the same compound. But because of the large thing that is present here, you are probably getting duped a little bit that these two positions are not same. So that's what I was thinking when I was writing this example, and that's when I thought that you should probably get a feel of this thing as well. Now, what is the green context? Reaction occurs in green energy source, so we are using microwave. Energy consumption, it decreases, it is more energy efficient. Reaction in 100% atom economy, that's not exactly the point here, because as long as you have price rearrangement, it will always be 100% atom economic. What is probably more relevant to write here is that the reaction has high yield, therefore the side products and byproduct formation is minimized. Process is cost effective and definitely eco-friendly. A lot of Claisen reactions has been done in water, in pure water. The first reported use of water in promoting Claisen rearrangement was back in 1970, almost 50 years back. They used many substrates, out of which this one is very interesting. This one is known as corishmic acid. Can you see the trans relationship between the two groups? See the trans relation?
Yes, sir.
Where is the 3-3 kind of thing? This is definitely not aromatic ring, so this is not a traditional aromatic Claisen. This is an aliphatic Claisen, right? So the CO bond is 1-1, right? Then what do you have? 2-3, and then what you have? 2-3. So we expect this union, we expect this migration, and we expect this migration. Look at the product. মিলেছে?
Yes, sir.
The stereochemistry is important. So I have written important in the sense that you need to get a feel of the transition state that operates here, and it's actually a both transition state, as you will see. But for your exam purpose, this is not important. Even if they ask you to give you an example of a Claisen rearrangement using water, you can give this example, but probably they will not ask you to provide the mechanism because it is a little bit complicated. So this is your product, right? I'm sorry, this is your reactant, right? Can you see the trans relationship of this oxygen and that oxygen? Is it evident?
Yes.
How do I know? Because I have a hydrogen here, right? That's projecting upwards, and I have a hydrogen here, right? So that's projecting downwards. What is the relationship of these two hydrogens? Cis or trans?
Trans.
So for sure, the other substituents that are present, namely the hydroxyl and the ether functionality, they are also cis or trans?
Trans.
They are also trans. But at this, in this conformation, sorry, in this conformation the reaction will not take place. So the ring will have to undergo some sort of a flipping movement, and when it flips you can see that now I can move the double bond here, you can move the double bond here, I can move the single bond here. Can you see that?
Yes, sir.
So that's like 1 1, that's like 2 3, and that's like 2 3. See the transition state? Single bond is forming, double bond is forming, double bond is broken, double bond is being broken, no, double bond is forming, double bond is being broken, single bond is being broken here. Get that?
Yes, sir.
I have redrawn it, this thing. This one is I am looking from the right side. If I look at it from the left side, can you see the boat? Can you see the chair form?
Yes, sir.
What is it? Is it not the chair?
Yes, sir.
Yes, sir.
So that's how the reaction goes. But I drew it deliberately because I wanted you to see that these reactions are, looking at this you might get the feel that how on green earth this is happening. How is it possible for this to have this kind of a union between the 3 3? Because it's so far apart. But if you draw the correct conformational isomer, then it becomes pretty evident that this reaction will take place. Now take a look at this. This OH and this Cu2H, they are on the same side, right, in the product?
Yes, sir.
And the same OH and the CH2CO CO2H, that whole stuff, that is actually on trans, right? So
Yes, sir.
in my transition state I have to justify that. So if this thing goes, this CO2H will go down and become cis with OH, right? OH and
Yes,
CO2H cis, because I have a hydrogen here only. And this whole CO CH2CO CO2H, this group is with respect to this OH, what is it? Cis or trans?
Trans.
Trans. So this is my product. Get it?
Yes, sir.
I will again reiterate, you do not need this. But I thought it was kind of beautiful, so that is why I included it here. Okay. Moving on. Another example where water is used. A very small concentration of pyridine is used, and at 60 degrees centigrade for 3.5 hours you do the reaction is in water, and this is again another aliphatic Claisen. So this goes like this. So this becomes an aldehyde, and you get a corresponding, depending upon the stereochemistry that you are starting from, because this is a chiral center, you are going to end up with either cis or the trans isomer, but the yield is 85%. The corresponding S star, that means if you don't take the sodium salt, you can take also the S star. They underwent the similar rearrangement. Allyl vinyl ether of and 2-hepta-3,5-dienyl vinyl ether. I have not written these things. The same 3 3 shift is obtained, but the result is best when you take 2:1 methanol water, and rates about is 40 times faster than it is found in when you are using acetone solvent. A special feature is that you don't need to protect any OH groups doing Claisen rearrangement when you are doing this thing in aqueous methanol. At 80 degrees centigrade for 24 hours, the yield is 88%. Can you see the 3 3 sigmatropic shift? 1 1 2 3 2 3, right?
Yes, sir.
So this one will migrate here, this one will go here, and this one will go here, right? So this part becomes CH2CHO, fine, and double bond has shifted here. But the most important thing is, let me ask you this question: is this a suprafacial shift or antarafacial shift? Is this supra or antara?
The supra.
Yes, the answer is correct. How do you know?
Uh, So because they are interacting from the same side.
Yeah, that's the definition of supra, but how do you know in case of this compound? You look at it and you say it's supra, but how do you know? See, if I take this ring to be planar, it is not planar, but let us take this to be planar, then the vinyl ether, is it towards me or away from me?
Away from.
And the CH2CHO group on the same ring, is it towards me or away from me?
So this is also away.
So do you get it? Why it is supra? Why is it
Oh,
supra?
yes, sir.
The
Yes,
same phase from which the migration has started, and the migration has also ended up, the sigma bond migration has ended up in the same phase, and that phase is the phase away from me. This ring has two phases, right? One phase is towards me, the hydrogen is towards me, and the other phase is away from me. So this is a substituent which is away from me. So eventually I will end up with this compound, and I will get this thing as my final product in high yield, doing an environmentally benign reaction medium at even manageable reaction temperature, not much of energy expended, and we are also getting we are getting the desired stereochemistry here because it's a supra migration. Okay. if you take, this is one interesting tidbit that is present here. If you do the Claisen condensation under usual Claisen condensation, then acetaldehyde is eliminated. How can a acetaldehyde be eliminated from the product? Can you tell me? How can acetaldehyde be eliminated? Under usual Claisen condensation, it results in elimination of the acetaldehyde. How is the acetaldehyde getting eliminated?
Sir, the CH2 because when we enter hydrogen on the carbon,
Which hydrogen? Which hydrogen do you expect to be eliminated? This one or that one? Can you actually tell which hydrogen? Because if you have like double bond here, then it's also conjugated, right? If you have double bond here, then that is also conjugated, right? So it's rather difficult to say which hydrogen, but again, both hydrogens are cis or trans with respect to the CH2CHO?
cis.
No. The CH2CHO is away from you.
Oh,
This
away
hydrogen
from.
and
Oh,
this
yes,
group,
trans.
they are trans. Both these hydrogens are trans, right? So elimination can happen from both sides, and you are going to end up with a tetrasubstituted double bond in both cases. So it's kind of difficult to say, at least from this form. If we could draw the actual conformational isomer of this, then maybe we could say something. But it's important to realize that there are certain hidden points in these relatively simple looking reactions that can spoil your party. So you think that you can do this thing in conventional method, you are not going to end up with this one at all. You are losing one acetaldehyde molecule and you are getting a conjugated diene instead of that desired thing. So they have modified this. The last example of today is the synthesis of fenestrine. This thing is known as fenestrine, right? This is fenestra means window. So if you have like 4 5-membered rings sharing a common atom between them, then that's called a fenestrine. This looks like a window. So in the synthesis of fenestrine, there are many steps. So this one of the steps was something like this, where they have done this Claisen rearrangement in aqueous methanol in presence of one equivalent of NaOH. The reaction time and temperature is not great, but as you are using water, the reaction is catalyzed. So 8 hours for a Claisen rearrangement is pretty low. In fact, as far as Claisen is concerned, it can take hours and hours. So again, this is 1 this is 2 3, this is 2 3, right? So this one goes here, that one goes here, and that one goes here, right? 3 sigmatropic shift.
Yes, sir.
Can you spot the supra?
Yes, sir.
Yes, sir.
Same thing. Started from behind, ended up in behind.
Behind. Yes, sir.
So, I would like to conclude today's class here and take up the further examples in the next class. If you have any questions on this, I would be happy to answer. Do you have any questions?
Sir, is it possible that the reactant means like here we are getting it supra, maybe here the reactant is behind, then we get a product which is like forward in front.
If you take the corresponding diastereoisomer, then that product can be formed. But for that you need to have this thing in front of the ring. You have to synthesize that.
Oh, okay, sir.
Because the reaction's restriction is that it has to go supra-supra. It has to be supra-supra. The supra-antara mode is actually geometrically forbidden.
Yes, sir. Yes,
So that is why you can't have this. You can end up with something like this on this side, but for that you need to have your starting material something like this. If you can manage to prepare that, then it's okay, no problem.
okay, sir. Thank you, sir.
Any more questions from anyone else?
No.
If it is not, then I am concluding the recording.